So guys, in the previous video, we have talked about the models required for performing the high-speed signal integrity simulations. Now, after performing the simulations, what are all the outputs we are going to get? We need to know, right? So, while we'll talk about that by doing the simulations in the tool later, we'll just give a glimpse of what are all the things that we'll be looking at. So, this signal integrity simulations can be done in two ways. One thing is, as we talked in the previous video, we'll have a driver, we'll have a receiver, and then ultimately what the designer need to know is whether there are losses in the channel or not, whether the signal is propagating properly from the transmitter to the receiver or from driver to the receiver. Now, to know that, there are two important parameters which characterize the channel. One is called insertion loss, which you see here, and the other one is called the return loss. So what is the difference? So we mentioned that in high-speed designs, you will have signals returning back if there is an impedance mismatch. We have talked about this in our previous videos. So because of this impedance mismatch, there will be reflections. That is first thing. And second thing, when you insert power from the driver, the channel will have some losses, which basically could be PCB trace loss, dielectric loss, okay, or so these are any power loss that is associated. All these could be uh, uh, like have drastic issues on the performance of the channel. Now, to calculate these two parameters, we have insertion loss, which is nothing but the logarithmic ratio of power transmitted by power received at the load. So we get to know how much power is being lost in the channel. Return loss is nothing but logarithmic of power inserted by power reflected. So you get to know the reflected loss, and then you have the power incident, and then you calculate the return loss. So insertion loss is called S21, return loss is called S11 in S parameters. So when you are doing simulations, the simulation engineer can directly take the channel and show you the insertion and return loss. So if insertion loss, return loss are satisfactory, you can say the channel is going to work without any issues. But let us assume you want to see how the exact waveform is. Like example, if we are giving a clock from a driver, let us assume 100 megahertz. So high speeds could be much higher in gigahertz, right? But we are considering 100 megahertz here. Let us assume 100 megahertz signal that is output from the driver, and this signal is propagating over the channel to the receiver. So clock, we know it's a 50% duty cycle with a specific level. The levels could be anything. It could be LVC, MOS, whatever signals you have, signal levels, signal topologies you have, as per the interfaces you use. These levels need to be maintained, and as we have seen in the previous videos, there should not be any overshoot, undershoot, there should not be any lumps or the monotonicity which we have talked. So all these should not be there. So to see how the waveform is, we probe at the receiver in the simulation tools and see how the signal is received at that end by simulating the entire channel. So in this scenario, in tools like hyperlinks or whatever tools you use, we have oscilloscope options where we can see the signal, we can probe the signal at the receiver and get to know how the signal has been behaving. And all the parameters like rise time, fall time, your maximum peak, average value, all these can be calculated in those oscilloscope tools, which is a very important tool, right? Whereas if you do just insertion return loss, you just get the loss associated in channel, but you get to know the actual signal parameters in the oscilloscope tools. Now, if you are not satisfied by just having one signal, one clock transmitted and then seeing that in the oscilloscope, there is another tool, another probability of checking the signal, the channel performance by using something called eye diagram. So eye diagram is we have talked about this in our videos. We will talk about in detail later. For now, remember that eye diagram is something which shows you the exact performance of the channel. So what happens is, to put it in a very simple terms, the eye diagram is formed by superimposing number of signals transmitted for a specific period of time, and that superimposed signals look like an eye. So by this eye diagram, which is formed by taking number of samples of the signal, we can get to know what is the jitter that is there in the channel. Okay. And we can also have the exact parameters which are required, which will fail. Like example, if you have lower threshold, upper threshold, the rise times, the fall times, all these can be used to form something called eye mask, and then we can see the signal performance using that eye diagram. So this helps us to know the performance of the channel, and if there is any intersymbol interference that is there in the channel. So the jitter which we see gives us an idea. Very useful tool. So if you see that in the oscilloscope your signal is good and there isn't an issue, people doesn't go to the eye diagram, because there itself it is very clear and your eye diagram works perfectly well, and it is okay because your signal doesn't have any anomalies, right? So if you see overall, these are the things which we see, which we get as a output from the simulations, and which helps us to analyze. So it's again at the discretion of the design engineer to understand the simulation results and take necessary actions in the design. Very useful tools, right, for a high-speed design engineer. So we will talk about more when we see the practical observations by performing a simulation. Thank you.